In April 2025, a surge of tectonic energy was released across multiple fault systems. A magnitude 7.7 in Myanmar, a 6.9 in Papua New Guinea, and a 5.2 in Southern California. These seismic events reflect regional stress fields that have been intensifying for decades. Behind these patterns is a deeper geodynamic story, revealed through high-resolution GPS, deep crustal imaging, and real-time Titan shield models. The sequence began with a powerful subduction zone rupture beneath Myanmar, followed days later by a strike-slip earthquake in the New Guinea highlands and a transform fault rupture near Julian, California. These events occurred in geodynamically sensitive zones, each within active plate boundaries with well-documented strain accumulation. Titan Shield integrates crustal velocity fields, seismic moment release histories, Coulomb stress transfer models, and fault zone rheology to forecast rupture probability. Prior to April, Titan Shield flagged Myanmar and New Guinea as Level 3 stress hotspots based on anomalies in GPS strain rate fields and subsurface density differentials. The magnitude 7.7 event occurred along the Indo-Burma subduction zone, where the Indian plate subducts obliquely beneath the Burma microplate. This zone has a history of megathrust earthquakes. The April rupture initiated at a depth of approximately 60 km, likely along a locked segment of the interface where interplate coupling exceeds 0.8. Focal mechanism solutions indicate reverse oblique motion, consistent with the tectonic stress regime in the eastern Himalayas. The 6.9 event in Papua New Guinea was generated by shear failure between the South Bismarck and Woodlark plates, a region with GPS velocities exceeding 70 mm/year. The crust here is intensely faulted, a mosaic of microplates caught between the colliding Pacific and Australian plates. The earthquake's shallow depth, strike-slip focal mechanism, and proximity to historical rupture zones suggest reactivation of a left lateral shear zone. Though smaller in magnitude, the 5.2 quake near Julian occurred on the San Jacinto Fault, which accommodates a significant portion of the Pacific North American plate boundary motion. In this region, lateral motion averages approximately 48 mm/year, confirmed by GPS arrays at Anza, Elsinore, and Borrego. The San Jacinto Fault is known for aseismic creep, but localized locking zones are capable of triggering moderate to large ruptures. During Q1 and Q2 of 2025, Titan Shield achieved 92% spatial accuracy and 83% temporal precision in its regional rupture forecasts. Its success is attributed to hybrid modeling, combining machine learning hazard layers with deterministic geomechanical models, including Coulomb failure stress tracking across over 2,000 mapped fault segments. Post-event modeling indicates increased stress along the Arakan-Yoma fold belt, portions of the Himalayan frontal thrust, and fault systems in western Tibet. In the Pacific, the PNG quake shifted shear stress toward adjacent fault splays near the New Britain Trench. These effects could trigger delayed ruptures within the next 30-90 days, particularly in regions with high fluid pressure or lithospheric thinning. Together, these earthquakes reveal a planet under increasing tectonic tension. Our models show that slab pull forces in the Indian Ocean, crustal thickening in the Himalayas, and slab rollback in the western Pacific are all contributing to an evolving seismic architecture. The Earth's lithosphere is not static, it flexes, fractures, and flows. Looking ahead, Titan Shield highlights elevated seismic probability in the Red Sea Rift and Afar Depression, the central Zagros region of Iran, and eastern Japan, where deep, slow-slip events may precede larger quakes. Each of these zones shares key indicators: rising strain, fluid migration, and changes in fault frictional behavior. I'm Ahmed Ben Mahfouz, geophysicist and independent researcher. As tectonic activity accelerates, our ability to forecast, warn, and prepare is only as strong as the models we build. Titan Shield represents a new frontier, one grounded in data, physics, and real-time analytics.